Hello everyone, welcome back to another lecture of fundamentals of ecology where we are studying population modeling. Okay. So, let us recollect what we sort of studied in the discrete time population model, especially the exponential growth, also called geometric growth, because we are studying populations that are changing discretely over time. So, we denoted Nk as the population size at kth generation, right, and if we denote lambda as the growth factor, which basically is captures the which is basically this formula where 1 represents the fact that we are accounting for the number of existing individuals in the current generation, b is the per capita birth rate, and d is the per capita death rate. D is a D should be thought of as a probability per unit time. In this case, unit time is 1 generation, therefore d varies between 0 and 1. Whereas b is a per capita birth rate, it is the number of offspring on an average that an individual produces. And with these definitions, we found that the number of individuals in the k plus 1th generation is basically given by lambda times the number of individuals in the kth generation. Okay. So, the key assumption here was that b and d were constants. Of course, this is going to be true only in some limited ecological contexts, and the most important one being that the resources are not constrained. This is true if resources are not constrained, or what we also call there is no limiting resource. Okay. So, that is when this is true. Now, what we will do in this class is to sort of study some implications, some numerical examples of how do we use this. Okay. Okay. So, let us start with a simple example which is often used. Example 1 is that of non-overlapping generations. So, what does this mean? This think of insects that lay eggs, and most of the parent generation dies off, and when basically the eggs hatch, what you have is a generation that has no parental generation that lives at that point of time. So, in other words, almost everybody in the previous generation therefore died. This basically means that lambda, which is 1 plus b minus d, has d goes to sorry I made a mistake here, b minus d. Since d is equal to 1, the first and the last term basically cancels off. So, the lambda is basically nothing but the per capita birth rate in this case, and therefore, the expression for how the population changes over generations is given by lambda nk, which reduces to b nk. Okay. So, in this specific case of non-overlapping generations, number of offspring per individual basically determines how the population is changing over time. Okay. So, let us now look at one more example. Okay. Let us look at an example such as cell growth, okay, cell division, where basically a single cell gives rise to 2 daughter cells. Okay. These are daughter cells, and this is the parent. So, in this case one way to think about how do we now use our previous formula. So, one way to think about this is one can think of maybe this as the parent himself or herself, whereas this is the offspring, right. But if effectively biologically once the 2 daughter cells are there, there is no distinction between these two, but keep that in mind. So, what that basically means is that the parent does not die, therefore, D is equal to 0, and the parent has given rise to 1 daughter cell, therefore, B is equal to 1. So, this means that lambda is equal to 1 plus B, which is 1, minus D, which is 0. So, therefore, lambda is equal to 2, and therefore, our expression for how population changes across generations will be given by nk plus 1 is equal to 2 times nk. Okay. Now, let us use this formula in the next examples to see how populations change over time. So, example 3, let us use this formula. So, remember that lambda is equal to 2. So, therefore, I could write this as 2 power nk 2 nk. Okay. So, now let us use this formula and apply it to some sort of with some reasonable numbers. So, for example, if you think of many cellular systems, let us think of an sort of hypothetical scenario where I start with at k is equal to 0 at the beginning of, let us say, an experiment that somebody is conducting. Let us say we had 1 cell. Okay. So, what happens at the next instance? So, 1 becomes 2, right, at k is equal to 2. So, now all that I have to do is effectively what I am now writing is on the second column here I am writing nk, and to get the nk plus 1 I have to multiply the previous entry by 2. So, this becomes 4 cells. So, each of the 2 cells give rise to 2 daughter cells, therefore, it becomes 4 cells. At k is equal to 3, each of the 4 cells will give rise to 2 daughter cells, so therefore, it becomes 8. At k is equal to 14, we have 16 cells, 32 cells, 64 cells, and so on, right. And in general, we can write, let us say, the formula as nk is equal to 2 power k times n0, where n0 was the number of cells at the beginning of the experiment. In this case, n0 was 1, and then nk is the kth generation, a number of cells in the kth generation. And in the, I think sometimes you will see different notations across books and so on and so forth. Some people may also write it as this, they are equivalent. There is really no difference between these two formulas. It is just a question of where is the starting point. So, in the second equation that I wrote on the right side here, in the second equation here, I am calling the first generation as n1, whereas here I am calling the starting generation as n0. Okay. So, but mathematically they are equivalent. Okay. So, we can use this formula to therefore determine how the number of cells are changing over time. And of course, for this formula to be true for all generations, remember that the birth rates and the death rates B and D, the per capita birth and death rates must be constant, and that would be true only when the resources are always sufficient for reproduction. let us continue to sort of look at some specific examples now. Now if you were to use this, how many cells are there at the end of one day? Let us do this simple calculation now. Okay. Remember that one generation was roughly equal to what, 20 minutes. Now depending on the the species of cells that you are studying, organisms that you are studying, this could really change a lot. Even within cellular organisms you can have 15 minutes, 20 minutes, 1 hour, and differing generation time lengths. So for the sake of example, let us consider this to be 20 minutes, okay, and that means that in 1 hour we have 3 generations, and in 1 day we will have 24 times 3, that is 72 generations. Okay. So using the formula that we derived in the previous slide, so we will have nk is 2 power k times n0, assuming n0 is equal to 1, and now the k at the end of 1 day will be 72 generations, right. So we will have nk is equal to n72 is equal to 2 power 72 times 1. In other words, the number of the population size of the number of individuals at the end of 1 day or 72 generations would be 2 power 72 cells. Now let us try to make some sense of this number 2 power 72. How big is this number? Okay. So to do that, notice the fact that first a useful thing to know for all the students would be what is 2 power k for k is equal to 0 to 10. Okay, please make a table, write down these numbers. This is something you must be quite comfortable with. Okay. So I will not do that here, I will leave that as an exercise to you, but note that 2 power 10 will be is equal to 1024, okay, which is approximately 1000, right. 1024, we can think of it as approximately as 1000, and we can write 1000 as 10 power 3. So therefore we can approximately treat 2 power 10 as 10 power 3, 1000. Okay. Now let us use this in evaluating how big is n72. So we will have 2 power 72, I can write this as 2 power 2 times 2 power 70. Okay. Again I can write this as 2 power 2 is 4, and 2 power 70 I can write this as 2 power 10 times 7, right, because 10 times 7 is 70. I have just rewritten 2 power 70 in this form. Now I know what is 2 power 10, I can use this expression here. So this becomes 2 power, sorry, so instead of 2 power 10 I will write this as 10 power 3 times 7. So this becomes 4 times 10 power 21. Okay. But of course remember that these are not exact equals. When I came from this step to this step, I made an approximation. So therefore I will denote this with a curly equals to indicate that there was an approximation involved. Okay. So basically that means that the number of the population size at the end of 72 generations or 1 day was roughly 4 times 10 power 21. If you were to actually use your calculator and do not make the approximation that 1024 is 1000, then you will actually find that the exact answer will be something like 4.72 times 10 power 21, which is not bad. We got pretty decent exactly close answer, and this is a useful trick to get some sense of what is the population size when you are dealing with really large numbers. Okay. Now let us now do one more example relating to this geometric growth, which is a bit of I think a fun example. Okay, so what is this example? Okay, so in this example, let us think of a beaker, okay, where I have put lots of resources for these cells to grow. Okay, let us say I start with one cell. So I have a beaker with lots of resources, lots of food for cells, okay, and introduce one cell like in the previous example, and now it will follow the same sequence of population sizes over time. 1 becomes 2, 2 becomes 4, at the end of 20 minutes we have 4 cells, sorry 2 cells, at the end of 1 hour you have 8 cells, right. You can even sort of at time t0 you have 1 cell, 20 minutes we have 2 cells, 40 minutes we have 4, 60 minutes which is 1 hour we have 8, okay. And then I can go on 1 hour 20 minutes I will have 16 and so on, okay. So here comes the question, here comes the fun part of the question, okay. So let us say I give you some information that at the end of one day the beaker was full, it was exactly full when it reached one day, okay. So the question is, when was it half full? That is the question. So now this is a question that you may have come across some puzzles and so on in high school, okay. And the reason why I am showing this is that it really conveys the power of exponential or geometric growth in a very interesting way. So how do we now address this? Okay, now of course when we have a beaker, it is a 3-dimensional thing, it is about volume of the beaker, right. But I do not know the volume of the cell. So maybe we can sort of start by assuming that each cell has the same volume, right. And then note that the beaker was exactly full, I mean the entire volume was occupied at 24 hours, right. Now if we assume that each cell has the same volume, we can sort of treat the numbers of cells and the volume that these number of cells occupy interchangeably, right. So with that key idea, so volume and the number can be used interchangeably or equivalent in that sense, in the sense of finding out when the beaker was full, right. So now remember that when the numbers were half of the current numbers, the volume must also have been half. So that gives us the idea, so we reached at 24 hours the beaker was full, right. And one generation before this, right, which was before 24 hours, the numbers were half, number of cells were half the current number, therefore the volume of cells must also have been half the current number, right, which basically means that at 23 hours 40 minutes, right, that is when the previous generation ended, right. It only takes 20 minutes for one generation. The beaker was half full, and this is quite interesting. This is something one would not naively expect, unless you think through it carefully, right. It was 24 hours, the beaker was full, and at the previous generation 23 hours 40 minutes it was half full. And this is really incredible, because if I go back to the table I made in the beginning, I had only 8 cells at the end of 1 hour, right, and then at the end of 2 hours, which would be 3 more generations, we would have had 8 became 16, 16 becomes 32 and 64 cells. In fact, if we had continued this, we would have found that it is only 64 cells. It is however incredible to imagine that in 1 hour what you are actually seeing is more than doubling, but if you only had to look at the numbers, it is really hard to get the sense of how these numbers are changing so rapidly. And it only took 20 minutes to go from half of a beaker to the full of the beaker. Now this has really huge implications for many environmental issues. Let us think of a simple example of an environmental issue such as landfilling, right. Let us say every year we are increasing the landfilling by some percentage, okay, and let us, for the sake of argument here, let us assume that every year we are doubling our landfilling capacity of the waste that we generate. Let us say we had 100 landfills, okay, and let us say that in 10 years we went from 0 landfills being filled to half of the 100 landfills being filled, okay. So 50 landfills have been filled, let us say at the end of 10 years. Now how much time will it take to now go from 50 to 100? It would just take now 1 year, it would not take another 10 years. That is the difference between a linear growth and an exponential growth, okay. So to illustrate this more precisely, it is useful to learn the concept of doubling time in a more general way. So I am going to talk about learning time, specifically in the context of geometric growth. So I am using the word, remember that I am using the word geometric growth to mean exponential growth, but with discrete generations, okay. So now let us understand what is doubling time in a general context. So in the previous examples of the cell division, 1 generation was the doubling time. That need not always be the case. Now let us look at the more general expression of this discrete time population model, where the birth and death rates are constant. In this case, let us understand doubling time. Let us say that T2, I am going to use the subscript 2 to indicate that the population size has doubled, okay. So let us say at the beginning we had at generation 0, so we have n0 individuals, right. Let us say at generation t we now have nt number of individuals. Let us say that the t corresponds, because we are interested in the doubling time, let us say this actually corresponds to doubling of the initial population size, okay. Let us say this is equal to 2n0. So the question is, how long does it take? We know the general formula is given by the expression above, right. So and in fact the general formula that goes between nk and n0 is given by this, right. And so if I now apply it to the exactly doubling time, so n t2 is equal to lambda t2 times n0, and remember that n t2 is twice the initial population size, therefore I can write n t2 as 2n0 okay. So I can cancel n0 on both the sides, okay, and then therefore we now have 2 is equal to lambda power t2. Let us now take the natural logarithm on both sides. So we will have logarithm of 2 is equal to t2 times logarithm of lambda. This basic, so since I am interested in how long does it take for a population to double, that I will keep on the left hand side t2, and I will put everything else on the right hand side. So that becomes logarithm of 2 divided by logarithm of lambda. What this formula tells us is, if I know the growth factor per generation lambda, I can calculate how long does it take for the population to double from this simple formula of logarithm of 2 divided by logarithm of lambda. Okay. So what I have done before coming to this class is made a table of how for various values of lambda how will the generation time look like. Now just remember one important thing here, lambda is basically 1 plus b minus d, okay. Lambda of anything more than 1 represents that the population is growing, it is because it is a growth factor, a factor that is more than 1 means the population is increasing, right. So basically we will assign various values to b minus d, which sort of represents the growth rate per generation, which we called r tilde in one of the previous classes, okay. So we will consider how this lambda influences the value, okay. So what I will now do is write a table where I will write down various values of lambda and the corresponding doubling times, okay. So let us consider lambda is equal to 1.01. What this really means is that on an average, if there are 100 individuals, they become 101 at the end of one generation, okay. So if that is the case, if it was a linear growth where if I add exactly one individual at the end of one generation without a multiplying effect, we would find T2 to be 100 generations. However, in the geometric growth what we find is that the doubling happens in 69.66 generations, okay. Somewhere between 69 and 70 generations the population would have doubled. Now let us consider lambda to be 1.02, meaning that on an average I am adding 2 individuals per 100 individuals at the end of one generation. Again, if it was a linear growth, it would take 50 generations to double, whereas in the geometric growth it would take 35 generations. I am writing here only up to 2 decimal places. If it was 1.05, meaning on an average we had 5 individuals per 100 population size per generation, it would take 14.21 years for doubling, as against 20 that you would have expected from linear growth. If it was 1.1, okay, then it would take only 7.27 generations, okay, to double. If it was 1.2, you would need only 3.8 generations to double. So this sort of shows the power of geometric growth. It is much faster than what we would expect by a simple linear growth, and that really is what distinguishes a geometric growth from linear growth. So we will stop here for today, but remember that what we have covered in terms of the exponential growth is using the discrete time assumption, and when we think of populations where there is no synchronicity in the birth and death processes, and if these the increases or decreases in the populations do not happen in bursts at discrete times, then we must really be using continuous time approximations. That requires some amount of calculus which we will discuss in an upcoming video. Thank you very much.